Hey, goedemiddag. Morgen, wat is het? Morgen. Je hebt geen geluid.
Dat klopt, er stond een rood streepje door mijn microfoontje heen.
Juist, oké.
Even kijken, ik ga eerst even mijn debiele Rijksuniversiteit Groningen weghalen.
Nou zeg.
Ja, hij past in ieder geval niet mooi in mijn beeld. Dus
Nee, dat klopt. Het is heel groot. Ja.
Even kijken, waar zit dat beest? Het zit waarschijnlijk hier, preferences. Zit het onder preferences? Ja, background. Hup. Wat dacht je van deze?
Nou, gezellig.
Ja,
Hey,
hè?
ik zie Mick Mulder zitten. En wie zijn die weer?
Zin, dat is...
Oh ja.
Ja, LHCB,
Ja.
LHCB-vrienden, hè? Maarten hier helemaal in de achtergrond nog.
Ja. En waar
Even
is
kijken.
dit?
Wat was dit? Even zien. Dit was, volgens mij was dit bij een of andere brouwerij in België, volgens mij. Bij een beefvis outing.
Het ziet er heel gezellig uit.
Ja, goed hè?
Ja, zeker.
Even kijken, maar ik doe gewoon even mijn echte achtergrond. Wat vind je daarvan?
Ja, prima. Dan zit je haar ook beter.
Ja, dank je.
Nee, dat is...
Jongen, oké.
Kijk, dit krijg je dus als je op een achtergrond zit, dan doet je haar allerlei rare dingen
Ja, dan krijg je zo'n spinnenweb, zo'n spinnenrag over je hoofd.
Ja. Hey, goed je te zien.
Ja.
Goedendag. We zouden heel even moeten checken of alles werkt. Nou, beeld en geluid gaat goed, volgens mij.
Oké, nou, dat is mooi. Even kijken, dan wil ik alleen nog even zien waar ik in godsnaam... Hoe lang had je mij toebedicht trouwens?
Nou, we hebben een uur. Maar als je denkt van nou, dat is wel heel veel korter, dan mag dat ook.
Nee hoor, ik babbel hem altijd wel vol. Even zien, ik had een prachtig praatje gemaakt. Waar heb ik die?
Wat ik zou voorstellen is dat we wel ruimte laten, zeg maar, voorbij de helft dan voor vragen en opmerkingen en zo.
Ja, kijk, daar komt de uitdaging. Hè?
Nou, weet je, anders dan zeg ik, als jij 3 kwartier onderweg bent ongeveer, dan zal ik een keer roepen dat
het nu toch echt wel genoeg is.
tijd begint te worden.
Ja.
Dan kijken we even hoe het afloopt.
Ja, laten we dat maar doen. Even kijken. Hup. Dan moet ik even oefenen, want wij zoomen normaal niet. Dat is dat even dat ik dat kan oefenen.
Bij mij staat onderin een groen knopje, dat heet Share Screen.
Ja, wacht even. Ik moet eerst even uitvinden waar ik het beest gelaten heb. Hier heb ik dat beest gelaten. Nikhef Lunch 2021. Het is toch prachtig. Hup, deze. Nou, dat is lekker. Maar PDF doet het nu al niet.
Ja.
Jouw prachtige plaatje vreet hij niet. Waarom niet? Even kijken. Hup. Ik dacht, ik steel jouw aankondigingsplaatje maar even. Dat is wel een mooi voorblad.
Dat mag natuurlijk. Maar...
Die vindt hij niet fijn. Waarom vind je die niet fijn? Replace. Nou dan, ben je nu gelukkig?
Heb ik iets uitgezet wat niet mag? Nee. Mooi.
Nou, dat ga ik zo meteen nog even mee prutsen.
Ja, dat is goed.
Even kijken. Ja, dus wat zeg je? Share screen. Ik kan hier share screen. Desktop 1, 2. Oh jeetje, dat is een handige. Even zien. Wat wil ik? LibreOffice. Hop. Wat handig joh.
Maar wat gebruiken jullie voor je meetings?
Ja, de rug heeft ziel en zaligheid verkocht aan Google. Dus wij doen alles in Google.
Ja.
Even kijken. Allow. Ja, zie, het is maar goed dat we dit even doen. Allow the apps below to record the contents of your screen, even while using other apps. Even zien, waar zit dit beest? Zoom. Oh, click to make changes. Ja, is goed. Jongen. Hop, zoom.
Doe alles om processen te voorkomen.
Zoom will not be able... Oké, quit and reopen. Dus ik ben even weg en dan ben ik weer terug.
Ja, oké. Ja, nu ben je wederom stil.
Stil, ja, nu niet meer. Wat lekker, hè?
Wat? Stil.
Dat ik even stil ben. Ja, kijk, hup, deze. Share.
Ja.
Wat dacht je hiervan?
Ja.
Ja, maar dan doet hij de hele window, of niet?
Ja, maar dan kun je hem nog op dia-mode zetten, toch? Dus
Even zien. Ja, dat kan. Zo.
yes. Nou, dat is prachtig.
Even zien, heb jij nu... Oh, dat is handig. Ik heb 2 schermen. Even zien. Zie jij nu zie jij mijn voorblad alleen, hè?
Ja, en ik zet jou in een venstertje daarnaast. En het klikken gaat goed zo te zien.
Even kijken. Dus dan krijg je bladzijde 2,
Ja,
3, 4.
ja.
Oké, dit moet dan even de animaties eruit slopen, want dat was helemaal niet de bedoeling. Ja, ik ga nog eens even streamline. Nou, allemaal mooie plaatjes.
Ja.
Hup, animatie allemaal eruit, zometeen maar. Nou, hoppatee.
Je hebt
Nou,
die slide van Patrick nog erbij, geloof ik, of niet?
ja.
Ja. Met helemaal rechts.
Ja, hier, even zien. Zie jij nu ook mijn muis?
Ja.
Valt daar nog wat aan te prutten dat hij wat groter wordt? Of ligt dat
Nee,
aan
maar
mij?
dit zie je wel op je scherm hoor. Dat gaat wel goed.
Oké, dat gaat wel goed.
Dat is het enige wat beweegt, zeg maar.
Oké.
Nee, prima. Dit werkt.
Het werkt. Nou.
Dus dan wilde jij nog even wat rommelen aan de slides misschien?
Ja, even kijken. Dus wat doe ik dus nu? Even zien hoor. Stop share.
Ja.
Zo. Ja.
Ik zelf zet even mijn camera dicht en mijn geluid uit. Maar ik zie wel wat er op het scherm gaande is nog. Want ik ben nog andere dingen aan het doen. Zullen we zo 5 voor of zo weer landen?
Ja.
Oké, tot zo.
Oké, joep.
Hoi. Dag Loek, goedemiddag. Ik kan je niet horen, geloof ik. Wacht even. Nou, dat zit niet bij mij. Gerco?
Oh,
Hi.
ik ben er weer.
Yes, heel goed. We hebben dat helemaal niet besproken, maar de bedoeling is dat we het in het Engels doen. Dat had je toch ook gewoon in je hoofd gezet?
Ja, dat had ik gepland.
Oké.
Het zou, in het Nederlands zou het toch een stuk lastiger zijn, denk ik.
Ja, dat is altijd even wennen. Ja, nee, heel goed. Maar meestal zeg ik het, maar ik ben het gewoon vergeten. Dat bedacht ik net.
Nou, wij zijn een Engelstalige universiteit, dus wij doen niet anders.
Ja, onderwijs is gewoon bij jullie in het Engels ook in Groningen?
De hele
Helemaal.
faculteit, ja.
Ja. Oké. Dat werkt ook? Dat was in het begin in ieder geval
alleen nu krijgen er heel veel studenten uit, want Brexit, hè?
Ja, precies.
Alle studenten die niet meer naar Engeland kunnen, zoeken dus nu hun heil ergens op het vasteland.
Ja.
En daar worden dus universiteiten uitgezocht met een Engelstalig programma, en dat zijn wij.
Ja, dus je hebt een toevloed aan studenten ook.
Een enorme toevloed.
Ja, is dat? Ook in jouw divisie?
Nou, de voorspelling voor de natuurkunde, gewone natuurkunde die we hebben, is dat die van een instroom van 100 naar 170 gaan.
Wow, oké.
Ja, precies.
Dat
dus dat is wel
aanzienlijk, zeg.
een uitdaging.
Ja, dat snap ik, ja. Om dat allemaal te accommoderen is natuurlijk niet, dat gaat niet vanzelf.
Dat gaat heel erg niet vanzelf, nee.
En dat is heel erg jouw werk ook.
En dat is ontzettend mijn werk om toch te zorgen dat dat wel kan gebeuren, ja.
Ja, ik snap het. Even kijken hoor.
Nou, een mooie uitdaging is dat.
Ja. Nee, dat begrijp ik. Kijk, hoe laat is het? Er nog een paar minuten voor. Dus we hebben de tijd.
Leuk, ik zie de hele NikhefK-club van heel lang geleden zie ik hier alweer boven in mijn beeld verschijnen.
Ja.
Je oude hadron-vriendjes.
Ja. Precies.
Nou ja, die horen er ook bij.
Ja, er is niks mis mee.
Nee, absoluut. Prima. Ik vind het juist wel leuk dat we zo'n over alle generaties heen publiek hebben elke keer.
Nou, dat zien wij ook wel. Dit is wel het mooie van die online colloquia en dergelijke.
Ja.
Je kunt iedereen overal vandaan halen. Je haakt zo even aan.
Ja, en zonder enorm veel inspanning en moeite kun je meedoen of kijken. Ja, zeker. Nee, dat is mooi. Hey Robert. Hello.
Hi, Martijn.
Yes.
Gerco, everybody.
Hoi.
Robert, I had a question. There will be a G-2 colloquium as well.
Correct.
Soon.
We will have a colloquium in June. It's foreseen. It got delayed, unfortunately.
Is the date set?
Not yet.
Okay.
We have been in touch with the speaker for a long time, and it got delayed as they wanted to wait to have the announcement, of course, but then also at the level of the organizations there was unfortunately some delay. But also it's not so bad to hear it again after a couple of months. And
that's true.
We are also thinking of attaching a theory colloquium to it, but it has not yet been confirmed.
Right. Okay. So
all these G-2 people are probably drowned by requests for colloquia. I remember it from my days where at some point in 1 week, I think I did 4 or 5 colloquia around the US at that time, which was challenging.
And that was the time when you actually had to travel to get somewhere.
I could fly back and forth to Europe for free then using my air miles. It was going crazy.
Oh. Sounds like a nostalgic look back and Man.
Okay, we're more or less having a crowd right now. I would suggest we wait for another minute or so, and then you can. I'll do a short introduction, and I'll leave the floor to you then, Gerco.
Okay.
Yeah.
Yeah, boy.
We have a nice, I see Patrick as well. The man with the graph.
Hello.
Hi, Patrick. Okay.
Marcel groot in beeld. Hey Marcel.
Yeah.
Veel plezier zo meteen.
Nothing but.
Yo, Gerco.
Hey, chef.
Chef
Okay.
Jeff.
Yeah, chef Templon. Yeah.
He taught me how to say baas correctly.
Goed hè? Weet je het oefenwoord nog?
What's this?
Met paashaas en verzamelaar.
Wow. You're doing great. You had some practice, I guess.
Mm-hmm.
Okay. Well, it's 2 minutes past 12. Welcome to all. What's Luke saying? Okay. Welcome to this lunch talk we have organized after the news of last week that came out about the G-2 experiment, which caused a lot of excitement, I would say, inside physics, but also outside physics, which is a good thing, I would say, to have some positive, hopeful news from physics, particle physics as well. It had been, well, at that point, not a long time, because the LHCb experiment was earlier this month also big in the news, which is also a great thing to see happening. But we thought it might be nice, especially because G-2 is somewhat removed from the experimental physics, at least at NikhefTV, but we have some connections nevertheless. So we thought we'd ask some of the people actually connected to the experiment to talk about this, and we found Gerco to do this talk. I'm really happy with him doing this talk because, well, I'm curious about the results, and at the same time, this connection is intriguing because it's far away, but in a way, it's close as well. Gerco, you're in Groningen right now, in your own apartment, I think. But nevertheless, working as a director of, what's it called in English?
The School of Science and Engineering.
Yeah, School of Science and Engineering. Much organizing going on, but still able to do some physics as well every now and then. You're connected to the LHCb experiment still. That's a connection to the new physics we're all looking for. Let's say, I'll give the floor to you. We do about 45 minutes of talk, and we have room for questions afterwards. Not during the talk, please, because on Zoom that gets messy every now and then. So without further ado, I'd like to give the floor to Gerco.
Okay, thanks. I'll make this work on this beautiful Zoom. Hop. There. Okay, and now everything is hop. Yeah. Okay, so Martijn, confirm that this looks beautiful to me, please.
It does.
It does. Okay, good. Now, so thanks for the invitation. It felt a little bit like being dragged out of the mud for stuff that I did a long time ago. Nevertheless, I was also very excited about this new result that came out, and I'll gladly say a few words about the ins and outs of the experiment. Mostly as we did it in the past. For clarity, I'm not involved in the current experiment, so mostly you will see pictures from long forgone days, but nevertheless, I'll try to make the connection to the results that we have now. Now, from the title, you can see that I was invited for being one or the G-2 expert, apparently, among NikhefTV. That's not entirely true. There's a whole bunch of us actually with a connection to NikhefTV and the Netherlands. So these are the people that I'm aware of with a Dutch connection that had something to do with the G-2 experiment. As you may know, it started a long time ago at CERN, where one of our famous Dutch Nobel Prize winners, Simon van der Meer, was already involved in the G-2 experiment. Now, unfortunately, him I've never met, but Frank Krienen, who also was trained in the Netherlands, yeah, I've had the pleasure to meet in my early days at Brookhaven. Now, so Brookhaven was the previous home to this G-2 experiment, and that is where the strongest connection to NikhefTV and the Netherlands is. So Klaus Jungmann, who you see down here, who's still a NikhefTV member, was together with Ernst Sichterman, who's now in Berkeley, but at the time had just completed a PhD at the VU. Were there to look into the magnetic field analysis and setup. There was the well-known Charles Timmermans, who's of course also still an active member of the NikhefTV family, who was mostly involved in the DAC, as I remember it. Then there was me dealing with the analysis. And even Max Bach, who may be known, well, at least to one of the current NikhefTV staff, who was an intern at the time. Now, out of these people, both Klaus and myself were also involved a little bit in the Fermilab experiment, mostly the preparations for the move and the initial setup. But at some point, we had to leave that behind. Now, that's the experimental connection in the Netherlands. Also, the theory end, which makes the possibility to interpret any experimental result. We happen to have a connection to the Netherlands because there, Elisabetta Palante, the current director of the institute that both Klaus and I are into, was involved. She was one of the theorists who calculated the so-called hadronic contribution, which I will say a few words about. And possibly there were other people with Dutch connections to this theme. So if I forgot somebody, I will be happy to know who they are. But these are the people that I at least interacted with mostly at the time. Now, so this G-2 story starts with the work of Dirac. So we will first look a little bit into where this G factor actually comes from and what it is. And it appeared in the work by Dirac, where he found that the magnetic moment mu is actually related to the spin of an elementary particle through a bunch of dimensionful constants who make it a magnetic moment, and then a dimensionless constant which goes by the name of G, which stands for the gyromagnetic ratio. And that parameter is precisely the G that we're talking about here. Now, what we now know is that then indeed, if you want to measure the magnetic moment, all the interesting physics, because the spin is what it is, the fundamental constants are what it is, all the interesting physics, you could say, is in this gyromagnetic ratio G, which for an elementary spin 1/2 particle actually takes on the value 2, and that is precisely 2, except for a tiny correction, which goes by the name of A, which stands for anomaly or magnetic moment anomaly, which modifies this value 2 by a little bit. And this anomaly, as I will show, is where all the interesting physics is. This factor 2, which really is a mathematical 2, so no uncertainty there. That 2 simply comes from the fact that we're looking at the spin 1/2 particle, such as the muon or also the electron. Now, something similar, which is also in the NikhefTV portfolio, is actually the electric dipole moment, which follows essentially the same reasoning, that the electric dipole moment is also related to the spin of a particle with the same set of fundamental constants, but then also a dimensionless, not gyromagnetic, but if you want gyroelectric ratio, which usually goes by the name of eta. And that eta takes on the value 0 in our current understanding, because any other value would mean that parity and time reversal symmetry are broken. Now, this is something that Steven Hoekstra, among others, could at some point also fill a whole lunch seminar with. Now, if we look carefully at this value of eta and the anomaly, that is the interesting thing. That is where all the exciting physics come from, and not so much the 2. So indeed, G minus 2, and if we're really careful, G minus 2 over 2 actually is the interesting property to look at. Now, so where does this anomaly then come from? Very shortly, that comes from radiative corrections, all the particles that participate due to quantum fluctuations in the interaction of, in this case, a muon with an electromagnetic field, and that interaction gets modified by all sorts of virtual particles, which we can try to catch, or which we have caught in the standard model. Of course, there may be many other particles flying around. We hope to all find them, all sorts of SUSY particles and what else not. And those will usually also appear in some form or other modifying the interaction of a muon with the electromagnetic field, and in that way appear in this magnetic moment anomaly. Now, so what you see here are obviously theoretical approaches indicating our understanding of nature as we have it. But by the time you start to measure this anomaly, of course, you're dealing with nature, and nature knows about all the particles that are there, and all will have their effect. And so by measuring, you really find out about all the possible particles that appear in nature. And then you can try to match that with theory, where you put in all the particles that you well, either know and love, the ones from the standard model, or all the ones that you're desperately trying to find as an extension of the standard model. Now, so if we first look at the anomaly of the electron, if we take the anomaly of the electron, our most frequently appearing a charged lepton, there we find that the anomaly, at least to our current level of precision, is essentially completely dominated by contributions which arise from QED. In other words, radiative corrections that involve photons and the charged leptons themselves. And as with every QED observable, then the electron's magnetic anomaly can be written as a power series in the fine structure constant alpha, or alpha over pi, actually, as it is mostly done in this business, each with an amplitude which you can calculate based on the corresponding Feynman diagrams. And there's many of them, one for the first order, 7 for the second order, and so on. It rapidly grows, and mind you, what I show here at the bottom is only a small selection of those. As it turns out, these amplitudes can essentially all be calculated analytically these days. When I made this slide somewhere around 2013, this last one was still only estimated. But if I understood it correctly, this one has now also been calculated analytically. And the errors that you see on here are simply derived from the uncertainty in the electron, muon, and tau masses that appear in these calculations. But in principle, these amplitudes could be calculated with, well, arbitrary precision depending on your patients. So this anomaly for the electron can be calculated with absolutely stunning precision, and it can also be measured, and has been measured with stunning precision, in something which almost sounds like something that an accelerator physics person could cook up, but which is really an atomic physics accomplishment, namely the creation of what is known as the one-electron quantum cyclotron. It is actually a device which literally has the size of a tabletop. If it were not for the fact that it is a ridiculously high table, this setup is, well, about 1 square meter in floor space, but then going up several meters. And with this one electron quantum cyclotron, it has been possible to measure the G factor of the electron, or to be more precise, the G factor divided by 2 of the electron, with a precision which is shown here at the bottom of 3 parts times 10 to the minus 13. In other words, 0.28 part per trillion, which is absolutely stunning if you think about that people can reach that precision. However, now this is the G factor and not the anomaly. So if we want to translate this into something interesting, for example, the fine structure constant, because for a while this G factor measurement was so precise that no determination of the fine structure constant was enough to predict this value from theory, and therefore the reverse was used. This measurement was used to predict the fine structure constant. Now, the fine structure constant, which was extracted at the time from this G result there, was only this 370 parts per trillion, and this is precisely the statement that I made before. It is in the deviation from 2, or if you divide by 2, the deviation from 1, where the interesting physics start, and that is here at the 3rd digit only, which almost precisely matches the factor 1,000 difference in relative precision. Now, so this value for the fine structure constant was for a while the most precise one, derived from the electron G-2. But then several other atomic physics results came up, which were derived from the recoil of cesium and most recently rubidium atoms, which were recoiling when they were hit by a photon. Now, there you find that there is a relatively simple relation between several fundamental constants and then several measurable quantities. For example, the Rydberg constant, which is known to 1.9 parts per trillion, the ratio of the rubidium mass and the electron mass, which are each known to, several tens of parts per trillion, and then something which could be measured in these recoil experiments. Now, I don't want to go into the details of how that works. It's absolutely fascinating. So if you're impressed by experiments that reach precisions of parts per trillions, I challenge you to read these papers. They're very readable. And the trick is there that by atom interferometry in a gravitational field, they're able to measure this last term here to a precision of 141 parts per trillion. And after these previous numbers, you may say that that looks rather disappointing, but still realize that this is something which is very, very precise. Now, this has been done recently and somewhat less recent. And that caused a little bit of a stir initially because the electron G-2 result, which is indicated here in red, seemed to deviate a little bit from the measurement with the cesium-133 isotope in the sense of how the fine structure constant was to be predicted. And interestingly enough, it went in the other direction than the deviation of the muon, which is something that fits in the picture of lepton non-universality. But the most recent result, which was again more precise, ended up here, the one for rubidium, which is again consistent with the result from the electron G-2, and that now has removed this possible inconsistency. Whether or not it will stay here and whether this is the definitive final answer, we will see, because I think these people are also still trying to get their numbers down. And anyway, Altogether, the fine structure constant, which determines the precision of the QED prediction of this anomaly, is very well established and more than precise enough to use in all sorts of calculations. Now, so this is the electron anomaly, which depends exclusively on QED in essence. There's a tiny other contribution. Where it gets interesting, and that is where the stir came from, of course, was if we start to look at the muon. And the muon, as you all know or should know, is quite a bit heavier than the electron, some 200 times, and that means it has another sensitivity to the various radiative corrections that may be there. So it is customary to express the anomaly of the muon in several components, which are determined by I think I should say the most complicated of the various interactions, and that means that there's a contribution which is related to QED, so leptons and photons. There's a term which is determined by radiative corrections that involve quarks, in other words, that require QCD to calculate them. There's even a term which depends on radiative corrections due to the weak interaction, so with virtual W's and Z exchange. And then, of course, and this is the holy grail, whether or not there's a contribution which can be assigned to new physics. And all these terms, except of course for the new one, because otherwise it would be old by now, can be calculated within our standard model. And if we look at their relative contributions, we find that for the muon, by far the largest contribution comes from QED, so virtual photons and electron-positron loops. There's a significant contribution from QCD at the level of 60 parts per million or so, and the weak interaction leads to a correction of order 1 part per million. But nevertheless, this is all within reach of the experiment, and the big question is whether there's something new to be seen. So if you manage to measure the anomaly very precisely, oh, that was too quick. If you manage to measure the anomaly very precisely, you have to make sure that if you want to compare that to your theory, that you have all three of these contributions well calculated. And in that sense, the anomaly for the muon is what we used to call a calibration point for the standard model, because it involves all the three interactions. Where it gets exciting is if there is any deviation from experiment and theory, because that would then be a calibration point, or if you want a straitjacket for any possible new theories, which typically are of this general scaling behavior, that a new contribution to the anomaly depends on the mass of the lepton relative to a typical mass scale of this new physics squared with some corresponding amplitude. And that then immediately makes it clear why we're so interested in the muon rather than the electron, and why QCD and weak contributions show up only for the muon and not for the electron. And that is because the muon is so much heavier squared. In other words, the muon is 40,000 times more sensitive to new physics, but also weak physics and hadronic physics than the electron. Now, so to calculate this, I already gave you a flavor of what the QED contribution looks like. That's thousands and thousands and thousands of complicated Feynman diagrams that need to be evaluated. Now, I don't have to tell anybody that calculations involving quarks and quark loops are notoriously difficult, and also weak interaction contributions are, well, let's say tough, as the understatement of the day. Now, for that, for a long time, many people have made all sorts of contributions in trying to get the best estimate. But following the result from 2013, it was decided to start something that goes by the name of Muon G-2 Theory Initiative, which is a collaboration of many, and explicitly not all, but many theorists which are involved in the calculation of the magnetic moment anomaly. Now, this didactically horrible sheet is actually showing what the mission of this this group is, with some connection to the results. So, what this group is focusing on is the fact that the QED contribution to the magnetic moment anomaly is by now dominated by an unknown alpha to the 6th term. In other words, this 5th order, which I already indicated, is now is now under control, and it's completely negligible, the uncertainty on that. The electroweak correction is something which has been evaluated not only at 1st order, but at full 2-loop contribution, and also there, since it's doable from first principle, the error is negligible. All the fuss, if you want, is in the hadronic contribution, which is by 1 or 2 orders of magnitude the dominant source of theory error. So that is where this group, but also other groups, have put in a lot of effort to calculate it. And to help make the comparison of the experiment to the theory meaningful. Now, to give you an impression, this is from one of the collaboration meetings of this this group. It's an impressive number of theorists working together to tackle, well, essentially a single problem, one number or one contribution to one number, in trying to understand it. And to see the level of complexity, I show you this table from their website. Again, this is not my work, but from this this one collaboration, where the previous experimental result is listed as a benchmark or as a reference, and you can see the various complicated and more complicated hadronic contributions listed here, together with the efforts that went into it. The important message that I want to relay here is that the original precision from 13 years, 13, 17, 18 years ago, which at the time was approximately equal to the theory error, that the theory error has by now been reduced to below the experimental error at the time through very, very hard work. Now, so at least there's one theoretical result out which, well, which has undergone a high level of scrutiny. And so perhaps now it's time to look at the old experiment in Brookhaven and make some connections to the new one. So the experiment is, in essence, extremely simple, and it goes back to well, the work from Larmor, early previous century, where it was observed that if you stick an object with a magnetic moment, could be a bar magnet, but it could also be a muon. If you stick it into a magnetic field, that then the magnetic moment, and therefore for elementary particles, the spin, will start to precess at a rate which is determined by the magnitude of the magnetic moment and the magnitude of the magnetic field in which you place it. And this is actually all the theory, in essence, that you need to understand, for example, proton NMR, the tool to measure the magnetic fields in many of the devices that we use. Now, so if you can do this with a proton, stick it in a magnetic field and watch its magnetic moment precess, you could do the same thing for a muon, and then you would end up with a well, with a relation that looks something like this, where there is the ratio of the muon to proton mass, the ratio of two frequencies that you could measure, one for the proton spin precession rate and one for the muon, and then the G factor of the proton. And with that, you could calculate the G factor of the muon if you were interested. Now, so these ratios are known to stunning precision. It's listed here. Again, this is old values. The proton G factor is also very, very well known. So if you could measure these two frequencies, you would be done and you would have a measurement of your G factor of the muon. But as I pointed out, that is not where the interesting physics is. You have to be in the third digit, because that is where all the vacuum polarizations start to show up. So this would be a very inefficient way where you first have to expend a huge amount of time to measure the first and the second digit after the decimal point in order to get to the point where the interesting physics is. Now, this is where the storage rings comes in. In the storage ring, clearly the relation between the magnetic moment and the magnetic field and the motion of the particle have to be taken into account. So the relation between the spin precession and those quantities is by far not as easy as it was for the Larmor precession, but you can create something which is fairly simple in the end if you pick your experimental conditions cleverly. For example, if you make sure that your particles go around in a circle and not in a helix inside a magnetic field, this term that sits here disappears, it gets to zero. Similarly, if there's electric fields around in your setup, which you may need to steer a particle, for example, it would also affect the magnetic moment because of relativity, and the lab electric field would appear as a magnetic field in the rest frame of your particle. But their nature is extremely kind to us, and that is because of this 4-factor here that you find in front of this relativistic magnetic field. And it depends on the boost factor, gamma, and the G factor of the particle that you're actually looking at. And for the muon, as well as for the electron and actually several other particles, it turns out that you can make this term here identical to 0 if you have a particle with the correct relativistic gamma with the right momentum. And for the muon, it turns out that this is for a gamma of approximately 30, which corresponds to a 3.094 GeV over C muon. And then you end up with only this very simple term that you have here, which depends, and this is important to realize, which depends not on G, but it depends on A. And A is this third digit in G for the muons. But annoyingly, it also still has a factor 1 over gamma there. Now, that factor 1 over gamma can also be eliminated by realizing that charged particles go around in a circle if you put them in a magnetic field. And there you find that it has precisely the same relation as the spin precession, except that you end up with a term which is precisely proportional to this 1 over gamma, but does not have the anomaly in there. So if you measure the spin precession rate as well as the cyclotron frequency, the revolution rate of a particle in a magnetic field, and you subtract the two frequencies, then you get this immensely simple relation here, the so-called anomalous spin precession frequency, which in a laboratory system is the rate with which the spin rotates relative to its momentum. In other words, it follows this pattern that I showed here with these purple arrows. And this spin precession or anomalous spin precession rate is proportional to the strength of the magnetic field, some fundamental constants which you get from the code data or the PDG or your favorite book if you want. And then it has the anomaly itself and not G. And the importance of this may not be apparent right away, but as I said, this is the third digit of G. In other words, it's 1,000 times smaller than G. And everybody who's been in any counting experiment knows that the precision goes as the square root of the number of events that you have. In other words, by this trick here, you've become sensitive to the third digit of G, where all the physics is, and by increasing your sensitivity by a factor 1,000, you've reduced your beam time request by a factor 1,000,000. And that is something that will impress funding agencies a lot, and actually makes it possible to reach such a precision. Now, so if you could measure the anomalous spin precession frequency, and if you could measure the magnetic field, you can very easily extract the anomalous magnetic moment right away. So you need a fancy magnetic field, and that is something that was built up at Brookhaven. Here you see a picture of the ring that we had at the time. It's a 280-inch diameter ring. Since it was built in the US, it had to have an inch radius, which corresponds to 7 meters and 11.2 centimeters of radius. It's a superconducting ring. It's the largest superconducting ring at the time of the world, and it's built of it's a single coil, which creates a very homogeneous and strong magnetic field of a little bit under 1.5 Tesla, which is the saturation point of typical steel. And that makes it possible to contain 3.1 GeV/c muons going around in this ring for a while. Now, there was a big stir, and around the time that Klaus and I left the experiment, because after Brookhaven was done, this ring was shrink wrapped and was put on a barge and on a boat and on a truck, and I don't think the helicopter in the end was used to transport it to Fermilab. So this magnet was transported to Fermilab, and there it was rebuilt with all the other measuring equipment, and this is a picture from Fermilab. Now, all the detailed improvements of the ring, I will leave that to whoever gives the colloquium. I think that was Mark Lancaster, if I'm not mistaken. A good catch. But it still looks the same. It's still equally blue. It has lost its thermal insulation, but it's still a hugely homogeneous magnetic field. The magnetic field was and is measured very precisely. So here is some of the tools that we had at the time, and many of those are still used today. So if you want to measure the magnetic field inside this storage volume, where usually the muons fly around, you have to find a way to do that as unintrusively as you can possibly do it. So here on the right, you see a cross section of the storage volume, and here in the middle, that is where the muons usually fly. And to measure the magnetic field, there are several probes, NMR probes, which rely on this Larmor precession I mentioned before, are mounted in the top and also in the bottom, which you cannot see because of this ruler here. So these probes here measure the magnetic field just outside of the storage region of the muons. To get it inside the storage volume, every now and then a so-called magnetic field trolley or NMR trolley that you see a picture of here is pulled through the vacuum chamber, riding on the rails that you see here. So these are the rails for the trolley, which are simultaneously used as electric field shaping devices. If you're thinking that I had a poor camera at the time taking a picture of this trolley, I should say that that is not the case. This trolley here is actually slightly bent, so it is not a tube, it's a banana, and it has a bending radius of 280 inches, 7 meters, and it's curved such that it fits nicely inside this storage volume. And it is also equipped with a set of 17 NMR probes, which are pulled through the vacuum while it is under vacuum in order to measure the magnetic field there. Now, with NMR probes, either in the wall or in this trolley, you get a relative measurement of the magnetic field. To make that absolute, as you need it, several so-called fixed probes are used, and a calibration probe is used to translate the relative measurements of all these NMR probes into Tesla, as is needed for the measurement. Now, so what comes out, and this is again old data, the new one you will at some point get to see, is something like this, where I've collected several pictures. For example, the magnetic field as it varies during the course of a run, which here takes of order of 60 days. You can track the variations of the magnetic field with time by looking at the various probes that you have. And you see that it is very fairly stable. Note here, this is a part per million scale here. So top to bottom is only 16 part per million variation. And you can see that the magnetic field goes up and down a little bit, but that is carefully measured. Here, apparently, there was some incident. And so this is how the magnetic field varies with time. If we follow one of the probes in the magnetic field trolley, you can see how the magnetic field varies going around the ring. Here, again, note that the top to bottom scale goes from minus 100 to 150 parts per million, which looks like an awful lot. But you can see that the magnetic field varies fairly regularly, actually. These are the cracks between the various pole pieces in the magnet that you see here. It varies around the ring for one of these probes, and since there's 17 of those, what you can do is make the average magnetic field map across the storage volume. So this now is the storage volume where usually the muons fly around. And there you can see that the variations go only between plus and minus 2.5 parts per millions in some very small edgy points at the end of the storage volume, where it should be set that the muons are usually flying around here in the middle. Now, so once you've made this this field map, you overlay the place where the muons usually are, and then you can calculate the magnetic field as experienced by the muons. For that, I want to use this this picture from Fermilab because it was so nicely presented in the recent paper. Here you can see through the contours that a similar homogeneity of the magnetic field was reached at Fermilab after this poor ring was transported through hurricanes across the Atlantic Ocean to Chicago, that it is still very, very homogeneous. And on top in these colors, you can see here now where the muons usually are. And you can see that they were, well, in this case, sitting somewhere in this region here, where the magnetic field does not vary by more than about half a part per million relative to the zero contour that you're seeing here. Now, so this made it possible to very, very precisely measure the magnetic field. Then we get to the spin precession frequency. This was actually where I was mostly involved in. And for that, we made use again of several gifts of nature, because really that is what it is. So we need spin polarized muons, which you may think are hard to produce, but in fact, they're very, very easy to make due to parity violation, which creates them highly polarized in the decay of pions. So at Brookhaven, as well as Fermilab, protons are accelerated, hit a target, and produce an enormous wash of high energy pions, which then subsequently decay mostly into muons and neutrinos. And because of the parity violating nature of that decay, the muons come out 100% polarized in the rest frame of the pion. Now, because of the boost, we have high energy, high momentum pions. What you find is that the emission angle of the muon in the rest frame of the pion translates into the energy in the laboratory, and that means that the original relation of the polarization of the muon is now connected to the energy that the muons have in the laboratory. So if you would select the highest energy muons that follow from the decay of monoenergetic pions, or the lowest, then you have a muon beam which is nearly 100% polarized. And indeed, in our time, the polarization of the muons was reaching 98% or so. So polarized muons are relatively easy to obtain. Now they're then sent into the storage region. You see the ring here, and there their spin starts to precess up to the point that the muon decays, and their parity violation again kicks in. The muon decays weakly, and that means that the emission angle of the positrons, in the case of a positive muon, are correlated to the direction of the muon spin. Now, the muons are again highly relativistic, so the angle of emission in the muon system connects to the laboratory energy of the electron. So by selecting the right energy electrons, the highest energy electrons in the lab system, you actually place a window on the emission angle of the electrons in the muon rest frame, and in that way you get sensitive to the spin orientation of the muon. Now, so these electrons are then detected through a set of 24 calorimeters, which looked like this at Brookhaven, and which were carefully redesigned and rebuilt for Fermilab. But again, I will not spend time on that. Now, so then you end up with a result that looks like this. This was 2003 Brookhaven results, where you see the count rate of high energy electrons appearing in the lab, which is nicely modulated with the spin precession of the muon. And what you see here is a plot of about 10 to the 10 events with cover 10 lifetimes or dilated lifetimes, and cover about 150 spin revolutions, which is then fit with a complicated function that accounts for all sorts of perturbations, but which in essence covers the function that I listed up here. At Fermilab, it looks quite similar. The colors are less pretty, I find, but okay, the plot looks quite similar. If you look carefully, you see a red line here, which is the fit on top of the data points, which are black. And for those of you who are into statistics, this is a fit with 4,132 degrees of freedom. And what is reached is a chi-square of 4,167. In other words, this is consistent with a chi-square of 1, a reduced chi-square of 1 at the level of the second digit, and precisely consistent with what you would expect from statistical fluctuations. Altogether, this is about 17 parameters or so that are fit.
Gerco, you have about 5 minutes left, okay?
Yes, yeah, I'm going to wrap up. So this then gives you the spin precession frequency together with the magnetic field measurement, then gives you the possibility to calculate the anomaly. And that is by defining something that goes by the name of R ratio, which is the ratio of the anomalous spin precession frequency to the proton spin precession frequency, the Larmor frequency. And what we did at the time at Brookhaven is use this ratio to calculate the anomaly as follows, using a parameter known as lambda, which is a measurement of the magnetic moment, the full magnetic moment of the muon relative to that of the proton. And this was a measurement which was performed by Klaus Jungmann and his collaborators at Los Alamos at some point. So this makes for a very easy measurement. At Fermilab, another approach has been taken. It looks somewhat more complicated. It involves the proton magnetic moment relative to the electron magnetic moment in a hydrogen atom relative to a bare one. It has the ratio of muon to electron masses and the electron G factor. So here we have the circle complete. We're back to the electron G factor, which was measured with a precision of subpart per trillion. And also the other components are of similar precision. Now, so then we can make the big map of experimental results, or mostly a progress of experimental results. It all started in '61 at CERN. I already indicated that. Then we at Brookhaven kept improving the experimental result, and now we have this Fermilab result. And what is particularly interesting, or at least to me, is that if you indicate at what point the various contributions were measured, QED was essentially immediately measured. The hadronic contribution, or the need for the hadronic contribution, was the goal of CERN in the end. Brookhaven was able to confirm the weak contribution with several sigmas of significance, and perhaps now Fermilab will get to the new physics. Hopefully, that would be exciting. Now, all these results together put us down to about 1/3 of a part per million, which is a quite precise result. Now then, the comparison with theory, because that is where all the excitement came about. That is this plot from the paper, where the earlier Brookhaven results and the new Fermilab results are plotted. And the first message out of that should be that these two results are consistent. That was, to me, one of the most important results of this new measurement. The Brookhaven and Fermilab results are consistent, and they're actually very consistent because what is indicated here is the statistical error with a tiny contribution of the systematic error at this point. So that is the first important message, and that means that we can calculate a single experimental average. And now if you want to compare that to theory, you have to decide which theory to use. Now, so what was chosen in the paper was to compare it to the Muon G-2 theory initiative, which is shown here in green. So it is a standard model prediction. And as you can see here, there's, well, quite a distance between that standard model prediction and the experimental result, which is at the level of 4.2 sigma. Now, to be fair, we should consider also other predictions. One which was published very, very recently by the BMW consortium, who relied on lattice QCD to calculate this hadronic contribution, in contrast to what the Muon G-2 theory initiative used. And that is summarized in this plot. So the other results are typically in range of these red points here, but this new lattice QCD result ends up somewhere over here, quite close to the experimental result, and there is no 4.2 sigma discrepancy anymore. Now, which of these two ones to believe is something that I will leave to the experts who know how to judge the quality of these theory predictions. But it is exciting to focus on the previous one where there was a discrepancy, and it nicely follows in a well, in this plot made by Patrick Koppenberg, very well known to all of you, where this new Muon G-2 result fits within the well, the wealth of almost consistent but not quite consistent, or possibly inconsistent results that we have now in the flavor sector on the leptons, compared to their respective theory predictions. And how this will turn out, well, we will see which theory is going to be able to explain all that. We will see. I'm pretty sure that in the following days, weeks, months, there will be hundreds, if not more, theory predictions on where this could come from, and I'm mostly curious to see that. Now, so with that, many statements, but I would leave you with this this picture. 4.2 sigma. It's a lot of excitement, justly so, because this is not consistent in our everyday world. But is this really the top of the iceberg, or the top of a new pyramid? We will well, we will see. And this will be explained in more detail in the near future in a full colloquium going into the Fermilab results. Now, with that, I will shut up and give the word back to you, Martijn.
Well, thank you, Gerco. Excellent talk. Very insightful. Thank you. I'm sure there's many questions. We actually, according to the clock, we only have 5 minutes left. So But still, we could go on for a while if people want to. Patrick has raised his hand for the first question. Patrick, go ahead.
Thanks, Martijn. So yes, that was very, very useful, actually. There's one thing I hadn't really realized is we're all excited that these two results are consistent. And everybody says now we have a second experiment that confirms the first Brookhaven experiment. But the key of that measurement is to measure the magnetic field, and it's the same magnet. So is it really a different experiment?
No, yeah, that is a very valid point. Clearly, the equipment used to generate the magnetic field is to a large extent the same. So the magnetic field, the coils, and so on, those were simply shipped from Brookhaven to Fermilab. The homogeneity of the field, which you reach by carefully shimming, is something which was completely redone at Fermilab. So in that sense, the intricate details and little variations of the magnetic field going around the ring and across the storage volume, those are all different. Now, then the magnetic field measuring system, because in the end that is where it mostly relies on, that was to some extent copied conceptually, but many of the probes were actually rebuilt with new readout electronics and so on. So conceptually, it was definitely the same. The hardware was mostly different. One thing which was shared, to my knowledge, but this could be wrong, is the usage of the absolute field probe. That is the relation between the relative field probes and the absolute magnetic field, and that is a very carefully crafted, incredibly spherical glass bulb, which was made in Heidelberg at some point. And there's only one of those on the planet that we or that they could use. But that probe has also been calibrated to an absolute helium-3 gas probe and confirmed to be true to what it says it measures. So in that sense, I think for a large part, the hardware and the methodology for measuring the magnetic field has also been changed from Brookhaven compared to Fermilab. And in that sense, most systematic errors, or systematic effects, I should say, that may have been left over from Brookhaven are likely removed. But what remains is, of course, the concept.
Okay, clear. Hella, you have a question?
Yes, well, actually, Max has a question. So.
Hey, Max, go ahead.
Hey, Max.
Hey, Gerco. Now I'm a little bit out of touch, but in the data-driven determination of a head, you could use either tau data or E plus E minus data, and there was a discrepancy there, at least a couple of years ago. I was wondering what the status of that is now.
Now again, I'm not a theorist, so I will just spread the rumor, and on top of that, I've not been following it very carefully. So, but indeed, the data-driven determination of the first order hadronic contribution could be done by two different approaches, either by using hadronic tau decay or by looking at the R ratio and E plus E minus hadron production. And there used to be a discrepancy between those two. Now that has been going back and forth for a while. The latest that I remember, which is admittedly from several years ago, was that at some point the isospin correction for the hadronic tau decay was carefully determined, because in the end, E plus E minus annihilation is a chargeless final state, whereas hadronic tau decay clearly takes over the charge of the tau. And what I remember from that is that at some point when the isospin correction was taken into account, those two data-driven determinations of the hadronic lowest order contribution came together. But for really deep, insightful ideas there, I think we should go ask a theorist to explain that in more detail. But the last that I know about it is that those discrepancies were resolved.
Okay, I'm quite sure that this will not be the last discussion of these results or future results. So we can have a look later on at this also. Any other questions? Marcel, go ahead.
Very nice talk, Gerco. I enjoyed it very, very much. I have a question also from the theory point of view. I'm not sure if it's a fair one to ask, but I'm just curious about it. And on slide 4 in the beginning, in fact.
Yeah.
We're almost there. And this diagram at the left bottom below, I see this neutralino running there. So anything could run there really, right? Now my question is, do you know that this thing has to be a scalar or can it also be a vector? Now, and there's a reason behind that question is because that's in LHCb anomalies we want to do things with vector type leptoquarks, right? So the question is this thingy, the sky zero bar that you have there on the left. Yeah, do you know, does it have to be a scalar?
No, I don't dare to say yes or no.
No, I'm just curious.
Of course, this is then also only the one loop diagram. So the complexities what go in there are beyond my understanding, I have to admit.
Yeah. No,
I would say to Marcel, go ask your local theoretician, right?
I was hoping there was one present here because my local one at the moment is just my living room. But okay. Thanks.
Still, there's many people that can answer your questions, I'm sure. So have a try. It's past 1 already. Let's say for a final question, anyone?
I'll happily answer any questions because you're only eating into my lunch.
Okay. Well, the point, of course, is that you will be available by email, etc. as well. So anyone with questions or afterthoughts, contact Gerco or others. From my side, I would say thank you so much, Gerco, for this excellent talk. I think it was really useful to get some more perspective on the news we saw last week. So thank you. I'd like to also thank the huge audience we had today, over 60 people, which is great. And I'd like to invite you to next week's talk, which will be a Meet the Neighbors talk. Someone from the Institute of Language, Logic and Computation, the director, of course, will take us into their research and tell us what the neighbors are doing at this point in time. So let's meet again next week on Wednesday. See you then. Stay safe and see you again. Bye-bye.
Yep. Hey, Ronald Staring. The whole Hadron crew was here. Wow.
Ja. Moest even, hè?
Gerco, ze zijn er gewoon allemaal nog.
Ja, jeetje, dat is gewoon een hele oude meuk van...
Ja.
Wat was dat?
Wat was dat?
1995 of zo, 93.
Zoiets. Ja, tot 98.
Vroeger, vorig millennium.
Ronald
houdt nog jong waren.
Computers in de lucht nu, hè?
Nog onschuldige kernfysici die waren. Ja,
Onschuldig? Nee, dat mag je nu niet meer zeggen. Hè? Kernfysica is nu, daar vinden we dingen van.
Oké.
Leuk verhaal, Gerco. Het was grappig om te zien. Ik ben natuurlijk, wanneer is het? 23 jaar geleden of zo heb je me rondgeleid op Brookhaven.
Ja.
Grappig om nu de theorie wat meer gestructureerd te zien. En ik kon het min of meer volgen, geloof ik. Dat is niet slecht voor een
Ik heb,
fysicus.
Ik heb mijn best gedaan. Nou heb ik dit praatje wat ik al zei. Hè? Toen we dat in 2003, toen wij dit bekend maakten. Nou echt werkelijk. Ik heb tientallen colloquia gegeven. Echt all over the place. Dus nou, dan krijg je op een gegeven moment de gelegenheid om een beetje te oefenen. Van wat werkt en wat werkt niet.
Ja. Nou, het was een goed verhaal. Ik bedoel, ik ben helemaal geen expert. Hooguit in de verte. En ik kwam een heel eind mee. Dus dat ging echt wel goed.
Nou,
Ik
mooi.
denk dat iedereen eruit pikte wat nodig was. Hey,
Ja.
ik ga de boel afsluiten.
Ja.
Jij nogmaals veel dank.
Ja, graag gedaan.
Take
Leuk.
care. En zoek vooral tijd voor je onderzoek ook. Zoals we al eerder bespraken. Is dat ook leuk om te
Ja, dat is toch even. Als we nou gewoon even dat virusje gewoon even uit de lucht weten te krijgen, dan komt dat allemaal weer helemaal goed.
Wordt een beetje aan gewerkt. Zullen we het zo zeggen?
Ja, is goed. Doe je best.
Goed. Iedereen tot ziens.
Ja, luidjes.
Tot
Leuk
gauw.
dat iedereen er was. Loek
Yes.
ook even goed om te zien.
De groetjes. Doei.